Hello viewers, in today's session we are going to discuss another important problem from Leibniz rule, which is differentiation under the integral sign. And here we have to solve this problem in which we are given a continuous and differentiable function f such that the integral 0 to 2x square f of t dt is equal to e raised to minus x square for all values of x belonging to the open interval 0 to infinity, and we have to find the derivative of this function f at this point, that is pi, right? So let us first quickly see the statement of Leibniz rule, and then we'll see how we can apply the concept of Leibniz rule to find out the value of f prime of pi, right? So first, our aim is to find out the function f of x, right? So once we get the value of the function f of x, then we can easily differentiate it, and we can get the required value of f prime of pi. So now the Leibniz rule says that the derivative, that is d by dx of the integral where the lower limit and the upper limit are functions of x. Let us take the lower limit as u of x and upper limit as v of x, and here we have a function of x and t and dt. Then the derivative of this integral with respect to x is given by f of x. Then we replace this t by the upper limit, that is v of x, and then we differentiate v of x with respect to x, and then we have the negative sign, and then we replace this t by u of x. Then we have f of x comma u of x, and we differentiate u of x with respect to x, and then here we have a term that is integral u of x to v of x, and we partially differentiate this function f of x comma t with respect to x. So now we'll make use of this statement to solve this problem. Now see, here we are given 0 to 2x square f of t dt is equal to e raised to minus x square, right? So what we will do, we'll differentiate both sides with respect to x, right? So differentiating both sides with respect to x, we have now a d by dx of the integral 0 to 2x square. Here we have f of t dt, and now we'll apply this rule to this expression. So now let us compare this integral with this one. So here the lower limit is 0, that is u of x is equal to 0, and the upper limit is 2x square, that is v of x is equal to 2x square, and here we have the function f of t, which is a function of t only, right? And here we have a mixed function of x and t, right? So now this expression is equal to f of x comma v of x. So here we have f of x comma vx, that is here we have only t, so we'll replace this t by 2x square, right? So here we have f of 2x square, and then we differentiate this function, that is v of x with respect to x, right? And then here we have f of x comma u of x. Now see, u of x is equal to 0, so here we have 0, so this entire term reduces to 0, right? And then we have this integral, that is u of x to v of x. Here u of x is 0, and then we have 2x square, and we have del of del x of f of x comma t. So here the function is of t only. So here we have f of t and dt. Now see here we have to find the partial derivative of f of t with respect to x, but this function f of t is only a function of t, so there is no x in this function f of t. So this derivative must be equal to 0, right? So this term is also equal to 0. So now we have simply f of 2x square, and here we can take this 2 in front of the derivative operator, and the derivative of x square is simply 2x. So we have 4x f of 2x square, right? So the derivative of this integral with respect to x using the Leibniz rule is equal to 4x times f of 2x square. So now this integral is given as e raised to minus x square. So we can now write d by dx, and this integral can be replaced by e raised to minus x square, right? So now we have this equation, that is d by dx of e raised to minus x square is equal to 4x times f of 2x square. Now the derivative of e raised to minus x square is e raised to minus x square, and by chain rule the derivative of minus x square is minus 2x. So we have now this equation, that is e raised to minus x square minus 2x is equal to 4x f of 2x square, right? So now we can cancel this 4 with this 2, and here this x and this x can also be cancelled, because here we are given that x is that is the x belongs to the interval 0 to infinity, so x is not equal to 0, right? So we can easily cancel out this x. So now we are left with minus e raised to minus x square, and here we have 2 times f of 2x square. So this is our equation. So now here we have a functional equation, and replacing this 2x square by some other variable, say y, right? So we can replace x square by y over 2. So now this equation can be written as minus e raised to minus y over 2, and here we have 2 times f of y, right? So f of y is equal to minus half and e raised to minus y over 2. So now again changing the variable y to x, we can now write our function in terms of x as f of x is equal to minus half and e raised to minus x over 2. So this is the required function, that is f of x is an exponential function, and here we have minus half e raised to minus x over 2. Now let us differentiate both sides with respect to x. So now f prime of x is equal to minus half d by dx of e raised to minus x over 2. So this is minus half, and the derivative of e raised to minus x by 2 is e raised to minus x over 2, and by chain rule the derivative of minus x over 2 is minus half, right? So this minus half multiplied with this minus half gives us 1 over 4, and here we have e raised to minus x over 2. Now taking x is equal to pi, because we have to find f prime of pi. So now f prime of pi is equal to 1 over 4 e raised to minus pi over 2. So viewers, the required value of f prime of pi is equal to 1 over 4 e raised to minus pi by 2, which can also be written as 1 over 4 e raised to pi over 2.